Hello everyone. So I'd like to talk a little bit about projectile motion. And just before we get going, I just want to sort of make a general comment, and that is that, first year physics textbooks, they're usually filled with particular projectile motion problems that you're asked to solve. So, a baseball starts here and it's thrown at an angle of 52.6 degrees with respect to the horizontal with some unknown speed. And then in the horizontal direction, say 20.2 meters away and, 4.6 meters up, there's a window over here. And you're asked to figure out, yes, how fast do I have to throw that baseball so that it hits that window? And when it hits that window, what is its velocity? What is its speed and direction and so on? So that's, an example of a particular projectile motion problem, usually involving numbers and so on. But I have to say that, generally speaking, physicists are not interested in such particular problems. What they're interested in is general problems. So they're interested, say, for projectile motion, they're interested in understanding everything there is to know about the general physics of projectile motion. And in general, for any kind of situation or system, you want to try to figure out everything you can know about it and just push the edges of that understanding in the hopes that you'll discover something new. That's how physicists generally work. So for projectile motion, what you want to do, usually in any kind of thing like this, what you want to do is find an example of the system that is as simple as possible and yet retains all of the essential physics. So for example, a general projectile motion problem, might look something like this. So there is a point here where you are going to launch the projectile, the baseball, and you make simplifying assumptions like ignore air resistance and all that kind of stuff to just sort of ferret out, understand the basic physics involved. So we say, yeah, starting from that point over there, we are going to launch a projectile with some, say, initial velocity vi. And that projectile will fly through the air on a parabolic trajectory. We'll talk a little bit about why that trajectory is parabolic, but the mathematical curve is a parabola. Okay, and so we'll go up like this. It'll reach a maximum height, and then it will come back down. So this is, say, the ground level. And, we could stop it at this point, but we're going to choose this point so that the initial and the final points are at the same level, and we have a great deal of symmetry to work with. So this is the simplest possible kind of representative example of projectile motion. Okay? And, we can label, say, the horizontal distance from the launch point to the point where it touches the ground again. This is the range. And the maximum height is, we'll call this capital H. And in fact, we're going to be interested in the maximum range and the maximum height as a function of this launch angle and the initial speed, okay, as sort of general relationships between height and range and angle and speed here. Okay, so this is our situation here. And now, because there is a preferred direction in this problem, namely the direction of gravity. Okay, gravity points straight down. So at every point along its trajectory, this projectile is experiencing a constant acceleration a, which is of magnitude g, pointing straight down. So a is equal to a constant. This is a constant acceleration problem. Okay, and so there is a preferred direction down. So when we're choosing our coordinate system, remember there's two things to choose. One is the origin. Well, obviously in this situation, we're not going to choose the origin to be here. We'll choose it to be at the launch point. So that's our origin. The next choice is what is the orientation of the coordinate system? Well, because we have a preferred direction down, let's align one of our coordinate axes with that preferred direction. Okay, so we'll take the y-axis, up, vertical up, and we'll take the x-axis horizontal and to the right. Okay, so then we can split our initial velocity vector v, I, into x and y components. So this will be the x component. This will be vx initial, which is v initial cos theta, and this will be the y component of the initial velocity, which is the speed vi times sine theta. Okay, so we have that. And then we say, okay, so what can we say about this just sort of immediately? Well, what we can say is we know that there is a force that's acting in the vertical direction, that's gravity, that's going to cause an acceleration in the vertical direction, and so the vertical component of velocity will definitely be changing. It'll start out large, it'll get smaller and smaller and smaller, it'll be 0 here, and then it'll start becoming negative, larger and larger negative. Okay? But in the horizontal direction, there's no force in the horizontal direction, there's no acceleration in the horizontal direction, there's no change in the horizontal component of the velocity. So whatever the initial horizontal component of velocity is, that will be the horizontal component of the velocity at every single point along its trajectory. So this allows us to actually right away start saying something interesting. So let's suppose that at this point up here, okay, so halfway up or whatever, we say, well, let's construct the velocity vector, just sort of graphically. Well, we know that the x component of the velocity will be exactly the same. That will never change. Okay, so this is the same as Vx initial. And then you wonder, well, what's the y component of the velocity at this point in time, at that point on the trajectory? Well, you can figure that out easily enough because you know that the velocity vector is always tangential to the trajectory. Okay, so it's in this direction. How long do I make it? Well, I make it long enough so that its x component, horizontal component, matches with Vx initial. And then I just go over like this and say, oh yes, that's Vy. That's Vy at this instant of time. And you just keep on going around. So at the top here, okay, what's the horizontal component of the velocity? Oh, we know immediately. That's never changing. That's constant. So that's the y component of the velocity. The x component of the velocity. It's the same as Vx initial. What's the y component? Well, it's 0. Okay, and then say down here, we have what's the x component? Well, it's the same as it always is. So this is Vx initial. What's the y component? Well, we know that the velocity vector is always tangential to the trajectory. It's in this direction. How long do I make it? Well, you make it long enough so that the horizontal projection of that velocity matches the Vx initial. And then you immediately can read off from the diagram, you can read off the y component of the velocity at this point in time. And similarly at the very end, you have this same Vx initial, and this is the direction of the velocity. Okay, it's actually the same as this. Let's make it the same. And so then this is going to be your final velocity. So this is V final. The x component of the final velocity is the same as the x component of the initial velocity. And you also see, because of symmetry, again, we're going to use the symmetry argument here, the y component of the final velocity, which you just read off of this picture here, that y component, Vy final, must equal negative Vy initial by symmetry. Okay, so here we're using symmetry. Okay. Now, of course, in general, we can't use symmetry. If our initial point is here, say this is t initial, so when we launch it, we say, ah yes, let's set t initial equal to 0. And then suppose our final point, our window is over here. The baseball is going to hit the window over here, and this is t final. Well, then you don't have that kind of symmetry, and then you need to look at the equations more generally, and we'll talk about that. Okay, so the most general sort of problem would be a t final, which is doesn't have this symmetry. Okay, we'll talk about that a little bit later. But for now, we're just looking at this symmetric situation, and that will reveal a lot of really interesting physics. Let's talk a little bit about the times. So t initial is equal to 0 here. And let's call the time that it takes to reach the top of the trajectory, let's call that time t equals t top. Okay? And then again, by symmetry, the time it's going to take to go from here to here will equal the time it takes to go from here to here. And so the time at this point, when it hits the ground, is going to be t is equal to twice t top. Okay, so t top, the time it takes to reach the top, will be one of the things that we'll be calculating and thinking a little bit about. Okay, so I think we've said everything. Or another just sort of general thing to say is that with this kind of motion, this projectile motion, you know, it goes up and it goes down like this, that motion is equal to two completely independent motions. One of the independent motions is just up and down. So if I take an object and throw it up and it comes back down, there's an up and down motion. And if there's no other forces and I throw this object, it will just drift horizontally. So if I take this up and down motion and combine that with a horizontal drift, then I get this projectile motion. So that's equal to just a strictly vertical up and down motion, plus where the velocity in the vertical direction is changing, it's large positive, and it gets smaller and smaller and smaller. It decreases momentarily to 0, and then it starts becoming larger and larger negative. Okay, so that's just a straight up and down motion with changing velocity, plus a horizontal motion, horizontal drift with constant horizontal drift velocity. Okay, so these two motions, vertical and horizontal, are completely independent, and we can look at them we can look at the equations independently and think about them independently and so on. Okay, so like I said, so generally speaking, in any kinematics problem, there are two kinematical equations, only two independent kinematical equations. Because this is a two-dimensional problem, they will be vector equations. So there are two vector equations. Each of those vector equations has two independent components, x and y, so you end up with four equations. Two vector equations or four sort of xy component equations. So let's look at those two general kinematical equations. So because the acceleration is constant, and that constant acceleration has magnitude g, which is a positive number, 9.81, and it is in the direction of negative j hat. Okay, so this is I hat and this is j hat in this picture. I hat running along the x-axis, increasing x, j hat running along the y-axis in the direction of increasing y. Because the acceleration is constant, we can take our general kinematical formula, which says that the change in the velocity v final minus v initial as a vector is equal to, in general, a average delta t. Okay, that formula is always valid. In the particular case where the acceleration is constant, well then the average acceleration is just equal to that constant acceleration. Okay, so we have that. And then we say, okay, now let's specialize this equation to, this is change between two times. Well, which two times? Well, let's take an arbitrary time t, say over here, and an arbitrary time t initial equals 0. And an initial time t initial is equal to 0. So this equation would read then the change in velocity, that's the velocity at some arbitrary time t along the trajectory, subtract the velocity at the initial time, so that's the velocity at time t equals 0. So that's the change in velocity. That's equal to this constant acceleration vector times this scalar, delta t. Delta t is the elapsed time. Well, if we start at 0 and end at time t, the elapsed time will be the final time minus the initial time, just that. Okay, and so what we get is this equation. The velocity at time 0 is this initial velocity vector vi. Bringing that over to the right-hand side, we have an explicit expression for the velocity vector as a function of time. So v of t is equal to negative v at 0 brought to the right-hand side is positive v at 0, so that's a v initial, plus the acceleration times t. Okay, so that we'll call equation number 1. Okay? And now this is one of the two fundamental kinematical equations, and because it's a vector equation in two dimensions, it's really equivalent to two equations. So we can take the x and the y, or the I hat and the j hat components of this equation. So if we take the I hat component of this equation, it's saying the x component of the velocity at some time t is equal to the x component of the initial velocity, so vx initial, plus the x component of the acceleration times time. Okay, so we proceed from the most general and then we make it more and more specific to the situation. You always do that. Okay, so and then we look at this equation and say, yes, but the acceleration in the horizontal direction is 0. There's no force in that direction. That means that just drops out to 0. And we have that Vx at any time t is just equal to Vx initial, and that's just a constant. Okay, so that's a constant. So let's just write it down below this. So this is, say, Vx at any time t is equal to Vx initial, and it's just a constant. Okay, so we can call this equation 1a. That's the I hat component. And yeah, so that's pretty easy. That's basically just telling you this. The velocity at any instant, the x component of the velocity at any instant of time is always the same. Okay, and then we can look at the j hat component of this equation, or the y component. So this tells you that the y component of the velocity at any time t is equal to the y component of the velocity initially plus the y component of the acceleration times time. Now the y component, we've chosen the y-axis to be vertically up, and so the y component of the acceleration is negative g. Had we chosen the y-axis to be vertically down, then the y component of the acceleration would be positive g. So in this case it's negative g, and so this is, let's just write this equation then below. This is just negative g, and so we can say Vy at any instant of time is equal to Vy initial, and then Ay is negative gt. Okay, and so this is equation 1b. Okay, now it's useful whenever you have any function of time to plot that function, okay, and see what you can sort of learn about the situation. In this case, the y component of the velocity. So we're going to plot Vy as a function of time. Okay. So this is time, and this is time 0, and Vy 0. Okay, and so this equation tells us that the y component of the velocity, the vertical component of the velocity, when t is equal to 0, is just Vy initial. So this is Vy initial. So it starts here. We also know that as time goes on, that velocity will just decrease, that vertical component of the velocity will decrease linearly with time, starting positive, passing through 0, and becoming negative. So it passes through 0 at this point, it's positive all along here, it passes through 0 at this point, and it becomes negative all along here, and maximally negative here. Okay? And so this is we know that at t equals t top, we know that the velocity is, the vertical component of the velocity is 0, and at twice t top, when it reaches this point, we know that the vertical component of the velocity is just equal negative the original vertical component of the velocity. So it's just symmetric. So it's negative Vy initial, and it ends up there. Okay, now we connect these dots with a straight line, and sort of a straight line. And so we just see that the velocity starts with a large positive value, and it just decreases linearly with time, and it becomes negative. Okay, so that's just throwing something up. When you throw something up, it has a velocity in that direction, but the acceleration is that way, which means the speed is getting smaller and smaller and smaller. And then when it's coming back down, the velocity is in that direction, and now the acceleration is in the same direction as the velocity, so the speed gets bigger and bigger and bigger in the downward direction. Okay, so that's that. And then you might say, okay, well, let's figure out what t-top is. How long does it take for the projectile to reach the top of its trajectory? Well, we know one condition. We know that the y component of the velocity, when time t is equal to t-top, we know that that's equal to 0. Okay, and so let's plug t equals t-top into this equation. This is Vy initial minus g t-top. And so that's one equation in one unknown, and we then solve for t-top. So the time it takes to reach the top of the trajectory is just Vy initial divided by g. Okay, and so that is a useful relationship. It's going to come in handy. And so we can just check dimensions. So velocity is a length over time. Acceleration is a length over time squared. The ratio of those two is a time. So dimensionally it's correct. And you can also see that if you increase the vertical component of the y velocity. If you double that, well, you'll double the time it takes to get to the top. So when I throw something up like this, if I double the initial velocity, it will take exactly twice as long to reach its maximum height before it starts coming back down. And if we live on a planet where g is stronger, for the same initial velocity, it'll take a less time to get to the top because the gravitational force is stronger, the gravitational acceleration is stronger. It'll reduce that initial velocity faster. It'll take less time to reach its maximum height. Okay, so this equation makes complete sense. Okay, and it's exactly the same equation you would get if you had no horizontal component of velocity and you were just dealing with, throwing an object straight up and straight back down. That's how long it would take to get to the top. All right, very good. So now let's move on to the second kinematical equation. So the second general kinematical equation also follows from just the definition. So this equation follows from the basic definition of acceleration as delta v delta t, and then there's a basic equation which follows from the velocity as delta r delta t. Okay, so we could use that equation, or we could take that equation and plug this equation into it and get a second version of a second independent equation. Okay, and so you're all familiar with this one. When the acceleration is constant, we can write delta r is equal to v initial delta t, and we derived this equation before, plus 1/2 constant acceleration a times delta t squared. And you're familiar with the x and y components of that equation, and that's the two-dimensional or three-dimensional vector version of that equation. Okay, so now we play the same game. This equation is independent of this one, so we'll generate another vector equation. So delta r, what does that mean? It means r at some final time, let's call that final time t, an arbitrary time t along the trajectory, subtract r at the initial time t is equal to 0. That's equal to the initial velocity vector vi times the time interval, which is the final time t minus an initial time 0, plus 1/2 the acceleration vector times the scalar t minus 0 squared. Okay, so it looks like that. And then we say, because of our choice of origin, the initial position in this coordinate system is just 0. Okay, later on its position is here. At some time t its position is here, and later time t it's over later times it's over here, and so on. But at t equals 0, the position vector is just 0. So that's 0. And yeah, so that's it. So then we write down, in general, we have, just to conserve space here, well, okay. So then we have this equation, which says that the position, an explicit expression for the position of that projectile, as explicitly as a function of time, is just equal to v initial times t plus 1/2 a t squared. Okay. So this is a second vector equation, vector kinematical equation that's independent of this one. There are no other equations you can write down that would be independent of these two. Okay, so then we do the same thing. We say, okay, let's take the x component of this equation and the y component. Let's see if we can squeeze them in here. So in the x direction, the component of the position vector in the x direction is x as a function of time. That's equal to vx initial times the time, okay, plus 1/2 acceleration in the x direction, but there's 0 acceleration in the x direction. Acceleration is in the y direction, and that's it. So x as a function of t is just vx initial times the time. Okay, so we'll call that equation 2a. And I wonder, yeah, let's put in equation 2b here. Okay, so, and then we look at the y component of this equation. So the y component of the position vector, well, that's what we call y of t. That's equal to vy initial, the y component of the initial velocity vector, times the time, plus 1/2 the acceleration in the y direction. The acceleration in the y direction is negative g. Okay, so it's a negative 1/2 g t squared.
Okay, so we'll call that equation 2b.
Okay, so we have two independent vector kinematical equations, 1 and 2, which split into 1a and 1b, and 2a and 2b. We have four equations. Okay, so in solving any projectile motion problem, you can only have four unknowns, and then you can solve for them using those four equations. Now let's take a quick look at this equation 2a involving x, and then we'll look at that equation 2b involving y. So they're both functions of time, and we will graph them. So this equation here says x as a function of t. It says that it starts when t is equal to 0 at x equals 0, and then it just increases linearly with time. That's because its horizontal motion is just drifting at a constant rate. Okay, and so x as a function of t is very simple. So it looks like this. So here is the time t, and here is the end time is twice t top, and this is t top, halfway, and this is 0. So when x is equal to 0, when t is equal to 0, then x is equal to 0. Okay, and then when the time is equal to twice the time it takes to get to the top, so the end time here, we are going to, the x position is what we call the range. So this is the range. And the x position just smoothly increases with time, linearly increases with time, and so we connect this initial and final point with just a straight line. And the slope of that straight line is just the x component of the velocity. That's how quickly it's drifting, how many meters per second it's drifting to the right. Okay, so we have that. And then we can we can get an equation for the range in this symmetric situation. Okay, so we say we know that the x position when time t is equal to twice t top, so t is equal to twice t top, that should equal the range. Okay, and so then we go and we look at our general expression for x as a function of time anytime, and we just plug in twice t top into that. So that's equal to Vx initial times twice t top. And we have an expression for t top down here. It's Vy initial over g. And so we get, we get a factor of 2. So we get, I'm going to write down the wrong thing here. So we get twice Vx initial, Vy initial divided by g. Okay, great. So that is the range. And let me just sort of write it, range equals. And that's going to be an important formula that we're going to use. Okay, now one thing that's interesting, so right away you learn something interesting about the physics of what's going on here. What you learn is that the range is proportional to the x component of the initial velocity times the y component of the initial velocity. That tells you right away that the range will be small if either the x or the y component of the initial velocity is small. So for instance, we have this kind of situation. If the y component is some nominal value and the x component is really small compared to that y component, well then the trajectory will look like this, and the range will be very small. Similarly, if you say have a given x component of initial velocity and the y component is small, like this, then you also know that it's just going to do like this. And so the range, I guess what I'm trying to say is you're launching it nearly horizontally. If you launch it exactly horizontally, then boom, it'll hit the ground right away. If you launch it nearly horizontally, it'll hit the ground very quickly. Okay, so the range is going to be small if either this or this is small. Okay, so that's an important and interesting thing. You can also check the dimensions of this. Velocity squared is a length squared over time squared, divided by an acceleration. A length over time squared gives you a length. So dimensionally, that's correct. Okay, so everything makes sense about that range formula. Let's now look at this y, the vertical position as a function of time. We know it's going to go up and come down as time goes on. And so let's graph that. So this is going to be the vertical position y explicitly as a function of time. So this is time. This is the final time, twice t top. This is the midway time, t top, and this is 0. And what we know is that the y position when t is equal to 0, well, that starts at 0. And we also know that the y position at the final time is also 0. Okay, so at the initial time and the final time it's 0, so we have those 2 points. But now we have something that, we have 2 terms. One of them is linear in time and one of them is quadratic in time. And that in itself is interesting. So if we turn off gravity, what it tells you is that the y position will just increase linearly with time at a rate equal to the initial y velocity. Let me try to draw this nicely here. Okay, so it just looks like this. So this curve is just Vy initial times t. So it says that if you turn off gravity and you throw something up, it'll just keep going up at a constant rate. So the y position will increase linearly with time at this rate Vy initial. But then we have gravity on. Gravity is causing an acceleration down, a free fall acceleration. And that free fall acceleration is a negative 1/2 gt squared. So for every time t, you have to subtract a negative 1/2 gt squared. And so you'll end up with a curve, that looks like this. And so when t is small, then the 1/2 gt squared is really small. But as t gets bigger, you are dropping further and further. When this amount of time has elapsed, according to just drifting up with constant velocity, you'll be that high. But then you've been free falling for that amount of time. And so this little part down here, that free fall portion, is negative 1/2 gt squared. And the interesting thing about this is that this t squared, no matter what the coefficients are in front, the 1/2 g or the Vy initial, whatever they are, it's completely irrelevant. A t squared will always dominate over a t for large enough time. Because this goes up like 1, 2, 3, 4. This goes up like 1, 4, 9, 16, 25. So this increases much more rapidly with time than this does. So this one will always dominate for large time. Dominate for large time. It's sort of irrelevant for small time, but it dominates for large time, and it will always take this linear curve and pull it down, okay? And it will eventually arc over, which just verifies the statement. What goes up must come down, and that's true. If gravity remained constant off the surface of the Earth forever up, then no matter how fast you threw something up, it would always come down. The fact that you have escape velocity and can actually escape the Earth's gravitational field is because Earth's gravitational field decreases in strength as you go further and further out. But if it remained constant, as the assumption in this problem, you see that what goes up must always come down. Okay, so that's kind of a cool thing that you kind of just see coming out of the diagram and all that stuff. Okay, so then the last thing we want to do with this is we want to figure out what is the maximum height here. Okay, so how do we do that? Well, we know that when time t is equal to t top, then y reaches its maximum value. So at time t equals t top, we know that the y value must equal the height h that we're looking for. Okay, so then we can figure that out. Let me just get rid of that. Okay, so what we have is from this equation, remember this is an explicit equation for y as a function of time. So let's take y at time t is equal to t top. Okay, that should equal the height h. Well, what does the equation tell us it equals? Well, it equals Vy initial times t top. What's t top? Vy initial over g. Subtract 1/2 g times t squared, t top squared. This squared, Vy initial squared over g squared. Vy initial squared divided by g squared. And you'll notice that these two terms are the same term. Okay, one of these g's cancels. This is a v squared over g. This is a v squared over g. 1 times v squared over g minus 1/2 times v squared over g is 1/2 times v squared over g. So it tells us that the height, the maximum height that the projectile reaches in general, is Vy initial squared divided by 2g. Okay, so that's another general. Where was our range formula? Oh, we haven't got that yet. Oh yes, no we do. Here's our range formula. Here's our range formula, and here's our height formula. These will be two important relationships that we want to look at. Okay, so we got that. And then of course you can just double check. dimensional analysis, a v squared is a length squared over time squared, divided by a g, length over time squared. That will give you a length. So dimensionally, that's correct. And you can also see that the height, in fact, you can just double check this very, very quickly. You can say, remember that the horizontal and the vertical components of motion are completely independent. So just thinking about the vertical motion, we've thrown some object up with some initial velocity vy initial. What does this equation say? Well, let's see. Let's multiply both sides of this equation by mg. The left-hand side becomes mgh. The right-hand side, there's a g up here, a g down here. You'll get a 1/2 mvy initial squared. Now that should be clear to you. This mgh is the gravitational potential energy that the projectile has at the top of its trajectory. And that's equal to the original kinetic energy, 1/2 mv squared, associated with its vertical motion. So kinetic energy at the bottom equals gravitational potential energy at the top. Okay, and so you know for sure that equation is right. It all makes sense. Okay. What else to say? Oh yeah, and so one other thing to say is we're now going to look at R and H in the case of this symmetric projectile motion. But let me just point something out, very important here, is suppose that your particular problem is, yep, launch the baseball over here with some velocity, blah, blah, and the window's over here, some distance, blah, blah, blah. Okay, so you're really talking about initial time here, final time over here. Okay, then you don't have that symmetry. But nevertheless, these two vector equations, this one and this one, are still true. Okay, and as are these four component equations. So when you're solving a projectile motion problem, a lot of the problem that I notice that you guys have is you've got some weird idea that there are 5 or 4, whatever, kinematical equations, and it's your job to memorize these equations and then, you know, in any given situation to try to guess which equation is going to be appropriate and so on. And then you end up sometimes using 2 equations that are not independent of each other. And then it just gives you, well, you just can't find the solution, right? And it's just sort of a mess. What I'm encouraging you to do is simply write down this equation and this equation, split it into x and y components, so you have 4 equations. This is a bulletproof, foolproof method of doing it. You have 4 equations, 1, 2, 3, 4, and then specialize those 4 equations to the particular situation at hand. You know, maybe the window is up here, and so the vertical component of the velocity is 0 when it hits the window. And so, you know, you look at, vy, here's vy. Where's Vy? Vy is a function of time, so when it reaches the top, that's equal to 0 or whatever. Then you start to specialize all of the variables in these 4 equations, and then you end up with 4 equations and 4 unknowns, and you just solve those equations. It's a bulletproof method of doing this. Okay? Anyways, enough about that. That's how you solve particular problems. But let's get on to the more interesting thing, which is talking about this range and this height in a little bit more detail. And I think we're going to run out of room here, so I'm going to, well, actually we can do part of it. Let's talk first about the range. Okay, so let's look at this range equation. Okay, so our range equation says that the range is twice Vx initial, Vy initial divided by g. And so we're going to express that in terms of not x and y components of the initial velocity, but in terms of magnitude like speed and direction of motion, angle theta. Okay, so this is 2 divided by g times Vx initial. Vx initial is the initial speed. Vx initial is the initial speed times cos theta. Times Vy initial, well, that's the initial speed times sine theta. So that's the initial times sine theta. Okay. And then, so this is, you'll recognize, and use a trig identity, you'll recognize that 2 times sine theta cos theta is the same as sine 2 theta. Okay, so I expect you to sort of know some trig identities, or at least know where to look them up. Okay, oftentimes in these problems you use trig identities to simplify stuff. Okay, so what you're going to end up with is V initial times V initial squared, divided by g, times twice sine cos, which is sine 2 theta. Okay, so that's the range. Okay, and now this is a really interesting equation. So the first thing to say about this is, regardless of the launch angle, Of course, the range will depend upon the launch angle. If the launch angle is small for a given energy of throw, well, the range isn't going to be very far. If the launch angle is really large for a given energy, it's not going to be very large. The range won't be very far, and so on. So it certainly depends upon the angle. We'll talk about that in a second. But immediately you see that it depends upon the initial speed squared. It depends upon the kinetic energy. Kinetic energy is 1/2 mv initial squared, initial kinetic energy. So the range depends upon the kinetic energy. So to double the range, whatever range you get, to double it for the same angle, you have to double the energy, okay? Which means increase the speed by a factor of square root of 2, okay? That will double your range. Also, it tells you that on a planet where g is larger, for a given energy and launch angle, the range will be smaller, which is obvious. Gravity is pulling things down faster. The acceleration is faster. It'll come back to the ground faster. Okay, so, and then we might ask a question like, okay, great. So how does this range depend upon the angle theta? Well, let's plot it. Okay, so this is the range thought of as a function of the angle theta. So what is that? Well, so the launch angle theta can range between 0 degrees, that's a horizontal launch, up to 90 degrees. Up to 90 degrees, okay? Or pi by 2. And so then we say sine 2 theta, where is the function sine theta maximized? When the argument of the sine function is 90 degrees. So we set 2 theta equal to 90 degrees. Sine of 90 degrees is 1. So 2 theta is 90, that means theta is 45 degrees. So at 45 degrees, this function is maximized. And what is its maximum value? Well, it's v initial squared divided by g. Basically proportional to the kinetic energy, the initial kinetic energy. Double the kinetic energy, you double the range for any launch angle. Okay, and you also know that when that theta is 0, sine theta is 0 when theta is either 0 or 180 degrees. Okay, so it'll be 0 here and it'll be 0 here. So it tells you what we discovered before up here, that the range will be small when either the x or the y components of the initial velocity are small. Here the launch angle of 0, here the y component is small, launch angle of 90 degrees, here the x component is small. And in those two extreme cases, the range is 0. Okay, and so the range looks like this. It's this sine function. Looks like that. And so obviously the angle theta for maximum range is then 45 degrees. And in that case, the range, the maximum range, at that launch angle of 45 degrees, then 45 degrees times 2 is 90 degrees, sine of 90, the range is going to be vi squared over g. Okay, so we have that. Yeah, good. But now comes the really interesting thing. Okay, this is super cool. Okay, so this is really what this is all about. So there's a bunch of stuff on here that we're going to need, so I'm going to attempt to erase this stuff. These light boards are super cool, but they're a little bit hard to erase. I found this awesome magic eraser, and it actually works not too badly. Okay, so remember, what we're doing here is we're trying to understand the nature of projectile motion in general. Okay, and so what we're going to do now, we've talked about the range and we've talked about the height. And what we want to do is take the ratio of those two, because that determines the overall shape of the parabolic trajectory. Okay, and we'll learn something interesting. Okay, so and let's also get rid of this. Okay, great. So what we're going to do now is we're going to say, we're going to calculate, we're going to imagine that we've got some trajectory here, and we're going to put it into a box. Okay, the width of the box, the width of the rectangle is r, and the height of the rectangle is h. And we're going to look at the aspect ratio, length to height, that ratio. Is it a tall, narrow box, or is it a squat, long box? Okay, so let's look at that. So let's take the ratio of the maximum height divided by just the height divided by the range. And how does that ratio depend upon the launch angle? When the launch angle is small, it'll be a wide, squat box. When the launch angle is large, it'll be a tall, narrow box. So let's see that coming out explicitly. So h divided by r. Here's our general expression for h. Here, vy initial squared divided by 2g. Vy initial squared divided by 2g. divided by the range. The range is, let's use this formula for the range, twice the product divided by g. So it's twice Vx initial, Vy initial divided by g. Okay, so first of all, you notice that these two g's cancel out. So it tells you that the overall shape of the trajectory is completely independent of what planet you're launching this on, Earth or the moon or whatever. Okay, so the g factor cancels out. Okay, that's an interesting thing to begin with. And so then this, you have a 2 in the denominator there and a 2 in the denominator. This is 1/4. And one of the Vy initials cancels out. And so you get 1/4 Vy initial divided by Vx initial. So the ratio depends upon the ratio of the y to the x component of the initial velocity, which you know immediately is going to be the slope. Okay, and so we can do that explicitly. So this is 1/4 Vy initial. That is equal to the initial speed, V initial, times sine theta. And Vx initial is this, which is the magnitude, the speed times cos theta, V initial times cos theta. And so now you will notice something else. You notice that the initial speed cancels out as well. So the ratio of height to width of that box range is completely independent of the initial velocity. Doesn't matter how fast you throw that. Okay, so if you throw it slowly, okay, and it goes like this, and you have a certain range of height, a certain ratio of height to range, if you increase the initial velocity, okay, you will have exactly the same shape of box, okay, except it'll just be a bigger box. But the ratio of height to width is going to be the same, independent of the velocity. So that's kind of cool. So this is 1/4 sine over cos is tan theta. Remember that tan theta is opposite over adjacent, so it's rise over run, it's equal to the slope. So basically the ratio of h to r is 1/4 the initial slope that you launch it at. And it's completely independent of anything else. What planet you're on, the g cancels out, what initial speed you have, all that stuff. So that's kind of cool. So so let me sort of draw a picture here. So if we take the case of 45 degrees, okay, so that's the angle of, that's the launch angle that will achieve the maximum range, as we figured out over here, everything else being the same. So when theta is 45 degrees, what we get is tan theta is equal to 1, and we have h over r, so we have h over r is equal to 1/4, and so let me put it this way, let me write it this way, r is equal to 4 times h. Okay, so that's sort of the representative example. And so let's draw that down here. So here is, we launch it at 45 degrees. And when we launch it at 45 degrees, it says that the range will be exactly 4 times the height. Okay, so let's just try to make it look sort of like that. So it'll look like that. So this is the height. Then the range will be 1, 2, 3, 4 of those. Okay, that's for 45 degrees. And then you say, okay, well, what's going to happen if we change this angle theta? So if we make theta, say, how should I say this? Suppose that the launch angle is now large. We take a large launch angle like this. Okay, and so if the large launch angle means large slope, so tan theta is approaching infinity, and so it says that the ratio of h to r is large. Okay, so that means for a given range, let's say for a given r, like this, it means that the height is large compared to that given r. And so the trajectory looks like this. So it's a tall, narrow kind of box in which the trajectory exists. If we take the launch angle to be small, the angle theta is small, then tan theta is small, the slope is small, and that means that the range is much bigger than the height. Okay, so for a given height, let's say for a given height, we're going to have a very large range. So suppose the height is this. For that given height, we're going to have a large range. Okay, so the box looks like this. Okay, it looks like a wide but not very tall box. And so the overall shape of the trajectory depends strictly on this launch angle theta. Okay, and that's it. Okay, so that determines the shape of the box. And then if you launch it with larger energy, remember the range and the height depend just upon kinetic energy. Okay, the range is just proportional to the kinetic energy. If you double the kinetic energy, you will double the range. Dunk, dunk. Okay, and then the angle determines the ratio of height to range. And so if this is, say, 4 to 1 or whatever, then it will be exactly the same, 4 to 1. And so this is what the trajectory will look like. Okay, exactly the same shape, but the box is exactly twice as big in both dimensions if you double the kinetic energy, the initial kinetic energy when you launch it. Okay, so that's super cool. So this is just an example of projectile motion, and what we're interested in physics usually is a general understanding of of a given situation, in this case projectile motion. So we went through sort of a general understanding of everything, but I also want to remind you that our discussion here is also applicable to particular solutions where you have baseballs and windows and stuff like that. You just use these 4 equations, these 2 and the other 2 that we erased from the board. Write those down first, and then start plugging stuff in particular to the situation you're dealing with, and then just solve those 4 equations. And you should have no trouble solving any projectile motion problem. All right, but I hope you find this kind of thing cool, because, yeah, that's what physicists like to think about. All right, very good.